In this video, we will try to imagine some of the technologies that could help first astronauts in the hypothetical colonization of Mars. We will try to understand the problems they might encounter and the possible countermeasures. The first big problem is to reach Mars alive. For a very long time, equivalent to no less than 6 or 7 months, the crew would be completely exposed to abundant quantities of cosmic rays and ionizing radiation, the effects of which in the long run could be deleterious to the health of the organism, with a consequent high probability of developing serious diseases. How to solve the problem by avoiding very heavy lead and massive radiation shields? At the Ames Research Center, California, they have developed and are testing a compactor that takes the daily non-organic waste produced in flight and converts it into a disc about 20 centimeters by 1.5 centimeters thick, which can be used to compose a light and very useful cosmic ray shield on the walls of the space capsule. A kind of tile in size which, thanks to the prevalence of plastic compacted at least 10 times in its constitution, can absorb the dreaded radiation and particles that run through the spaces between planet and planet. By carpeting one of the spaces of the spacecraft, for example, the sleeping area, or even creating a refuge area to be used for short periods in the event of a violent eruption by the sun, astronauts could be protected without having to carry the weight of a traditional shield made of thick metal. It could reasonably be objected that the waste could be thrown out of the capsule, an effective solution, although certainly not elegant and contrary to NASA ethics. Full of bacteria and other potential pathogenic agents, like everything in contact with humans, they could contaminate other planets. What would you do about it? Write it in the comments. The compactor is quite small and brings the material to a temperature of 150 degrees for 3.5 hours, a procedure sufficient to eliminate any microorganism, but not too energetic to risk burning the material itself. To make a 20 centimeter round shield tile, you need half a kilo of typical material for life in space, such as water bottles, plastic tape, food wrappers, aluminum, and foil packaging. There remains the problem of understanding how long the compressed material can last, and above all, given that it is used to upholster environments in which humans stay for months and months, if a healthy or at least neutral environment is created. This system would also solve at once another important problem related to space missions, namely the storage of waste produced by the crew. An alternative project proposed by NASA is water walls, which plans to use drinking or wastewater to protect astronauts from cosmic rays. According to Marco Durante of the Technical University of Darmstadt, water is better than metal as a protection because nuclei are responsible for blocking cosmic rays, and water molecules made up of 3 small atoms contain more nuclei per volume than metal. Furthermore, the water used as a shield can be drunk without danger, even if it has been extracted from human urine and feces. Water walls, in fact, involves the use of polyethylene bags which, through an osmosis process, will purify the water, constantly supplying astronauts with drinking water. These bags will form a 40 centimeter thick protective layer and will initially be filled with potable water, which will gradually be replaced by water recycled from the crew's organic waste. The Water Walls project also involves the use of bags capable of purifying the air from excess carbon dioxide, regulating the temperature of the shuttle, or creating microhabitats for the growth of plants and algae. However, many problems still remain to be solved. Although the bags have already been tested in orbit during the shuttle's last flight, their effectiveness in a microgravity environment is 50% of that demonstrated on Earth, not enough to keep a crew bombarded by constant doses of radiation alive. In the case of solar flares, probably not even a 10-foot thick concrete shield would be able to protect astronauts, explains Ruth Bamford, a researcher at the Rutherford Appleton Laboratory and responsible for the design of a magnetic solar radiation shield. To overcome this inconvenience, the last stage of the launch rocket could be kept attached to the shuttle, orienting it towards the sun during events involving substantial emissions of radiation. Once landed on Mars, astronauts will have to face another important problem: the production of energy and biofuels for the missiles that will be used to return to Earth, exploiting as much as possible the resources in situ: carbon dioxide, sunlight, and ice water. According to a process described in an article in Nature Communications, 2 terrestrial microbes would also need to be imported to Mars to start the bioproduction process. cyanobacteria, which would absorb CO2 from the Martian atmosphere and use sunlight to create sugars, and Escherichia coli, designed to convert those sugars into a specific propellant for rockets and other propulsion devices. This combination already exists on Earth and is called 2,3-butanediol. It has a formula CH3CHOH2 and is used to produce polymers in the rubber industry. Current rocket engines, which will reach Mars in the near future, are powered by methane and liquid oxygen, LOX, but neither exists in abundance on the red planet. This means that astronauts would have to receive them from Earth to return home, but the transport is very expensive. It is estimated that the journey of 30 tons of methane and LOX costs about $8 billion. NASA and other studies have suggested some alternatives to derive the two elements on the spot, but these technologies are still immature to work on a large scale. The Georgia Institute of Technology's proposal calls for in situ resource utilization based on biotechnology that can produce both propellant and LOX from CO2. The process would also return 44 tons of excess clean oxygen that could be stored for other purposes, such as supporting human colonization. First of all, plastic materials would have to be transported to Mars to build photobioreactors the size of 4 football fields. Cyanobacteria would grow in reactors via photosynthesis, which requires carbon dioxide. The enzymes in a separate reactor would break down the cyanobacteria into sugars for Escherichia coli, from which the rocket propellant would be obtained. This would be separated from the fermentation broth with advanced techniques. If for some reason this process fails and therefore it is impossible to return to Earth, how would you behave? Write it in the comments. Be sure to join the channel, leave us a like, and click on the bell. You will help us to make products of even higher quality. Pamela Peralta Yaya, one of the study's author and professor at the School of Chemistry and Biochemistry and CHBE, who engineers microbes for the production of chemicals, argues that this process needs much less energy to take off from Mars, which has given the flexibility to consider different chemicals that are not designed to launch rockets to Earth. Ways to exploit the planet's lower gravity and lack of oxygen have begun to be considered to create solutions that are not relevant to Earth launches. The team is now looking to perform biological and material optimization identified to create a linear and fast process. For example, improving the rate at which cyanobacteria grow on Mars would require a smaller and smaller photobioreactor, significantly lowering the payload needed to transport equipment from Earth. However, experiments still need to be performed to show that cyanobacteria can actually be grown under Martian conditions, and to consider the difference in solar spectrum on Mars due to both the distance from the sun and the lack of atmospheric filtering of sunlight. High levels of ultraviolet could damage cyanobacteria. Another issue of fundamental importance for the survival of a human crew is the production of oxygen. The Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, mounted on the Perseverance rover, has shown that the production of oxygen from the Martian atmosphere is possible. For the future of Mars exploration, oxygen will be a crucial element not only for the life support of astronauts. The rockets, in fact, also work powered by liquid oxygen, and to leave the red planet, it is necessary to be able to produce the propellant locally. MOXIE extracted 5 grams of oxygen from the Martian atmosphere for the first time. This is another historical moment for space exploration. But how is it possible to extract oxygen from an atmosphere that does not have any? Only 0.16% of the Martian atmosphere is in fact composed of oxygen, O2 to be precise, but this is not what MOXIE has extracted. The NASA instrument activated for the first time on April 20th during Sol number 60 collected carbon dioxide, CO2, which represents 96% of the atmospheric composition. Once it collected CO2, MOXIE has broken it down, collecting oxygen and releasing carbon monoxide into the Martian atmosphere. The experiment is another technological demonstrator, as the Ingenuity helicopter is therefore not a real scientific experiment. The experiment is placed inside the Perseverance rover and is about the size of a toaster, weighing 17 kilograms. As mentioned, the goal is the conversion of carbon dioxide into oxygen and carbon monoxide. The first is stored, the second expelled into the atmosphere. With this first activation of MOXIE, 5.37 grams of oxygen was produced. This amount is equivalent to about 10 minutes of breathing air, but MOXIE was designed to produce up to 10 grams per hour. To carry out this conversion, it uses solid oxide electrolysis, compressing and heating the Martian atmosphere. This process requires particularly high temperatures, which reach 800 degrees Celsius. The whole structure of MOXIE is therefore carefully built to support these temperatures and to isolate them as much as possible, as so not to damage Perseverance. Some components are made of nickel alloy, which support both heating and cooling of the collected gases. This is also an external golden coating to reflect infrared radiation and prevent them from radiating outside. MOXIE will now operate in 3 different phases to test it in as many conditions as possible. First of all, the condition and operation of the instrument itself will be checked, and the production just carried out is already an excellent first result. Then the test will be repeated in different weather conditions, such as different times of day or season. In the third and final phase, MOXIE will be taken to the limit, testing it with different temperatures. NASA has estimated that 4 astronauts will need about 7,000 kilograms of fuel and 25,000 kilograms of oxygen to leave Mars. It is unlikely that 25 tons of oxygen could be brought to Mars directly from Earth. A stay of 1 year on the planet would instead involve the consumption of about a ton of oxygen by the astronauts. For this reason, NASA itself is already thinking about the successor to MOXIE, a similar experiment but scaled in size. A similar instrument weighing 1 ton could produce about 1 kilogram of oxygen per hour. Such an instrument could produce 25 tons of oxygen in 3 Earth years. It would be enough to have 5 or 6 of these devices to reduce the time to 6 months. Another technology that cannot be missing from manned Martian missions is a 3D printer. Given that shipments with supplies will arrive every 26 months, the astronauts will have to be completely self-sufficient and able to build spare parts and tools on their own. A group of engineers from Northwestern Engineering's Tissue Engineering and Additive Manufacturing Laboratory demonstrated the feasibility of producing objects using synthetic replicas of lunar or Martian dust. Using Martian regolith, a series of simple solvents, and a biopolymer, it is possible to make special 3D printer inks to print a series of Lego-like bricks. The synthetic dust particles used in the laboratory have a composition, shape, and size very similar to those of the Moon and Martians. The 3D objects, tools, and bricks were then printed with a simple extrusion process. These similar bricks can then be used as building elements. The researchers assure that the tools produced with this method are flexible, elastic, but at the same time robust. The material can be manipulated, cut, or round and is very similar to rubber. In short, it could be suitable for use on the planet Mars. The next step will be to make this material as hard as ceramic, and the only possible way is to cook it as it is done on Earth in ovens. What other new technologies come to your mind for the colonization of Mars? Write it in the comments.